In last week's lecture, we looked at deep neural networks. One category of deep neural networks is convolutional neural networks, and that is what we're going to look at in today's lecture. So convolutional neural networks are commonly known as CNNs or ConvNets. A lot of the work done in convolutional neural networks has actually developed as a result of the ImageNet challenge. You'll see a number of the convolutional neural network architectures that have been developed for the challenge and have been winners for the challenge or runners up for the challenge. So, for example, AlexNet was one of the winners for the ImageNet challenge, and once AlexNet was developed, this actually took forward the whole field of CNNs very, very rapidly. So the one area that CNNs are very good for and work very well for is image classification. Another area is natural language processing. So we're going to base whatever we do in this lecture in the context of image classification. So if we're looking at image classification, we spoke about classification in the other types of neural networks that we looked at, for example, the perceptron learning algorithm. And if you remember, your classification could be binary classification, whether something belongs to a class or not. Alternatively, it could be multi-class, for example, which class an entity belongs to. So if you're looking at flowers, maybe a rose or an iris, etc. Now, if we look at classification in the terms of image classification, there's two types of output that your neural network can produce. The one type is what the class is, and that's for binary classification. So does it belong to the class or does it not belong to the class? You can also have multi-class classification where you're looking at which class it belongs to. Alternatively, and this is done very commonly with CNNs, instead of actually outputting the class, you output the probability of that entity belonging to each class. So for example, suppose you had three classes, dog, cat, and horse. Then if you actually input an image, for example, to the CNN, the output of the CNN would be an array of three probabilities. One probability, the first probability indicating the probability that the image belongs to the class dog, the second to cat, and the third to horse. So this is a little bit different from what we've been speaking about previously. So if we are applying a CNN for image processing, there's some pre-processing that usually has to be done. So when your image is input, it's input as a matrix of pixels. So if you're dealing with grayscale images, essentially you have a 2D matrix. That matrix contains integers, and those integers range from 0 to 255. If you're dealing with color images, we work on RGB. So you've got 3 steps 2D matrices, and again the range of the pixels are 0 to 255. The size of your input matrix that's representing the image is dependent on the resolution of the picture you've taken. So the higher the resolution, the bigger the matrix is going to be. And for that reason, sometimes pre-processing is done. You'll often see when you read about convolutional neural networks that pre-processing was done to reduce the image to a 512 by 512 image or 224 by 224 image. And the reason for doing this is if the images are too big, it requires too much of processing. As you'll see, a convolutional neural network is made up of a number of layers. The idea is to reduce the input at each layer as you progress towards the output layer. But if your image is very, very big, despite this, you can end up doing a lot of processing. Another thing you'll find that in order to implement CNNs, you need a distributed architecture, and usually GPUs are used to implement it, mainly because it takes so long to process. So the idea here is it could take even longer if your images are larger, and that is why pre-processing is done to reduce the size of the image. So one thing you'll find when you're working with CNNs, which is a little bit different from the other neural networks that we looked at, and again, this is also to reduce processing time, is if you looked at your previous neural networks, we said they're fully connected. So every input mapped to every output, and there was a weight that had to be calculated for each input-output mapping. But when you're dealing with CNNs, that's not necessarily the case. Not every input will map to every output. and we say that the inputs and outputs are sharing weights. So to look at the difference, if you look at the neural network on the left, that's a neural network, typical neural network that we've been looking at. So when we looked at applying the backprop algorithm, when we looked at the Hopfield neural network, when we looked at the perceptron learning algorithm and the perceptron neural network, basically this is what we've had. So if you look at your inputs, they range from x1 to x5, and your outputs are from s1 to s5. And you'll notice that every input is mapped to every output. And during the training process, the way the neural network learns is by actually finding weights for each of those mappings. But if you look at the neural network on the right-hand side, you'll see that's not the case. For example, x1 is only mapped to output s1 and s2. Similarly, x3 is mapped to output s2, s3, and s4. So in that case, we say the neural network is sparsely connected. And this brings in the whole idea of parameter sharing, where you find that inputs and outputs are now sharing parameter values, and your parameters are being your weights. And you'll see that is done by means of a feature map that is output for a particular layer, but we'll speak about that a little bit more just now. So if you think of the neural networks that we've looked at, we usually start at an input layer, and then we move from that input layer. If you're looking at a multi-layer neural network, you could have some hidden layers in between. So you could have one or two hidden layers, and then eventually you move to an output layer. So the main way in which learning happens is from the input layer through to the output layer, and at that output layer, that is where the activations of the neural network happen, and that's where you get your output. If you're applying an algorithm like the backprop algorithm, if that output is not what is specified in the target output in your training set, then usually there's some error propagated back through the neural network. So the way a CNN works is slightly different. So you have your input layer, but remember your input layer is now not just a layer, but it's a matrix. It's a pixel matrix that contains integers from 0 to, in the range of 0 to 255. From that layer, the next layer that it usually goes to is something called a convolutional layer. So we're going to look at what a convolutional layer is just now. Other layers that can be contained in your CNN include a nonlinear layer. That's the main reason behind your nonlinear layer, is to introduce nonlinearity, and that's done by applying an activation function. Usually input into your nonlinear layer is also called a ReLU layer because it uses the ReLU activation function. Input into your non-linear layer is usually from a convolutional layer. So usually a nonlinear layer will happen after a convolutional layer. The first layer in the CNN is always your convolutional layer. Another type of layer that can be contained in a CNN is a pooling layer. So usually the sequence in which these layers occur is convolutional, nonlinear, and pooling. The whole idea behind pooling is to further reduce the dimensionality as you go from one layer to the next, so that you have less learning to do and less processing to do. The last layer is usually a fully collected layer, and that joins the last hidden layer to the output layer. And sometimes you may find the layer just before that is also fully connected, and this is the typical type of fully connected neural network layers that we've dealt with when we looked at the perceptron neural network and when we looked at applying the backprop to multi-layer neural networks. So remember, when we train our neural network, the main thing that we're doing is we've got to determine the weights. So with all these layers, we move in a feed-forward fashion like we did previously when we were doing learning. And the idea is to determine an initial state of a set of weights. Initially, these weights will be randomly chosen like we've done previously. And then some optimizer will be applied to then propagate the error back through the neural network to update the weights based on the error if it's not producing the right type of output that we want. So in this case, the output will probably be in terms of accuracy rather than in terms of whether the target output matches the activation of the neural network. So the convolutional layer, this is the first layer after the input layer. You can have convolutional layers deeper in your neural network. So again, you can have them after maybe a nonlinear layer or after a pooling layer as well. So what happens in these layers? Now, if you remember previously, we applied, the way we actually obtained outputs is we multiplied, we took a weighted sum of the weights and the inputs, and sometimes we added a bias to that, then we applied an activation to that, and then we've got the output. Now here the layer works, the convolutional layer works very differently. It doesn't do matrix multiplication. It basically applies a convolutional operator, and that operator is applied together with a kernel or a filter. So the kernel or filter is actually a weight matrix in this case, or it represents your weight matrix. So a kernel is usually a 2D matrix. If you're working with 3D, then you're using a filter, which is made up of more than one kernel. And the whole idea is you use your convolution operator, so you perform some type of convolution at a convolutional layer. And that convolutional operator you apply together with this filter or kernel. Initially, these weights in the filter or kernel are randomly selected. Those two combined will then give you the output for that layer. And the main aim is to reduce the dimensionality of the output. The output that you produce is then called a feature map. So for each convolutional layer, you have a feature map produced, and the feature map normally is represented as a matrix as well, and it normally has a lower dimensionality than the input layer, especially if your convolutional layer is the second layer in your neural network. We spoke about sparsely connected and fully connected. So your convolutional layer is a sparsely connected layer, which means you're going to have mapping sharing weights, and those mappings will occur in your feature map. So there have been some convolutional operators or convolution operators defined, and these have been operators that have been derived by researchers. So common ones are things like the identity, the edge detection. You're going to play with this a little bit in the tutorial tomorrow. So often these operators aren't used on their own. They're usually used in conjunction with a particular kernel or particular filter. So remember, your filter or your kernel represent your weight matrix, and the initial values can be randomly chosen. Alternatively, if you want to achieve a particular operation in producing a feature map, then you can use human-derived kernels or filters that researchers know will produce a particular output. So especially if you want to use identity, you want to use that convolution operator, then you will use it together with a particular kernel. And like I mentioned, these values can be randomly selected, or you can use human-derived existing kernels or filters. So the way the whole thing works is you basically have your pixels. So if you can visualize, we'll look at an example just now. You have your pixel matrix, which contains integer values, and then you've got to apply some convolution to it using your filter. So what happens is your filter gets mapped to the pixel matrix, and the mapping process starts from the top left-hand corner, and you work actually through the input matrix from the top left-hand corner to the bottom right-hand corner, mapping the filter matrix across, and then working out the equivalent value. And you'll see just now we take the dot product and produce the reduced value in your feature map. So usually you move this. So if you decided that your filter or your kernel is going to be a 3x3 matrix, you will start at the top left-hand corner. Usually the dimension of the filter or kernel has to be less than the dimension of your input matrix or your pixel matrix, and often your feature map is the same dimension as your kernel or your filter. So you then move mapping this against the input matrix. You usually map it moving one pixel at a time. The number of pixels that you actually move during the mapping is something called the stride. The default value for this is 1. However, you can actually have a value of 2. This value is never ever, in most research, this value is not greater than 2. I think some studies have used 3. So if you had to use a stride of 2, and we'll look at an example just now, it means when you're mapping and you're moving that window or that square that's equivalent to the size of your filter, you actually going to move 2 pixels instead of 1 pixel, which means you're going to jump over 1 pixel. But we'll look at how you can do that just now. Sometimes before you apply your convolutional mapping to get your feature map, sometimes zero padding is added to the input matrix, so the pixel matrix, and whether to actually add this or not and how appropriate it is problem dependent. And we spoke about parameter tuning when we looked at genetic algorithms and when we looked at genetic programming. When it comes to neural networks, we don't say we tune parameters, we say we tune hyperparameters, especially when it comes to CNNs and DNNs. So zero padding, whether to do zero padding or not to do zero padding, is actually a hyperparameter to be decided, and whether to use it or not is problem dependent. So the steps in creating your feature map for a convolutional layer: firstly, you've got to decide on the dimension, and this as well as a hyperparameter. You can decide on the values that form that kernel initially, so these can be randomly selected, and in the example we're going to look at, we're going to randomly select this, or can be a known existing filter or kernel that performs a particular operation. So the other idea behind this is that if you look at the learning process, as you're moving from the input to the second layer, which is a convolutional layer, you're trying to learn certain aspects of that picture or that image. So it could be an edge, it could be a particular curve in the picture, and the whole idea is by deciding the size of your filter and what filter to use, you're actually deciding what learning is taking place. So you then apply the convolution to produce the feature map. And the way we achieve this is by mapping the kernel across the pixel matrix to produce the feature map, and we'll look at an example now. So if you look at the input matrix, you'll see I've displayed it twice because we're going to look at creating the first 2 digits of the feature map. So your feature map is also a matrix. So input matrix in this case represents some image, and it's a 5 by 5 matrix. You can see the size of the kernel is a 3 by 3 matrix, and those values have been randomly selected. The idea is that your feature map will also be a 3 by 3 matrix in this case. So if we look at how we calculate the first value of the feature map. So first we look at the sliding window that we're speaking about, and because we're looking at a 3 by 3 kernel and a 3 by 3 feature map, we have to map the kernel against the top left-hand corner of the input matrix. And so what we do is we take the dot products of both those matrices to find the first cell value for your feature map. So that will be the value that will be in position 0, 0. So if you look at that, you're taking 1 times 1, we're going row-wise, plus, which is 1, plus 1 times 0, which is 0, plus 1 times 1, so that gives us 2 so far. We move on to the second row, so that's 0 times 0, plus 1 times 1, which will give us 3, plus 1 times 0, which is 0. We're now on the third row. 0 times 1 is 0, 0 times 0 is 0, and 1 times 1 is 1, which gives us 4. So the first digit in our feature map will be 4. We now move that sliding window, we move it in a left to right, top to bottom manner. And here our stride is 1, so we won't jump over any pixels. We're going to move to the next pixel. So remember, the next pixel will then correspond to the next column in the same row in your feature map. So if we look at the sliding window now, if we had, so notice our rectangle begins at the second one in the first row, but suppose you had a stride of 2, then your rectangle will begin at the third one. And similarly, if you were going vertically, if you have a stride of 1, the row that you would start at is the row 0, which is straight after the first row. But if you had a stride of 2, you'd start at the third row, which is the second 0 in the first column. So if we look at now this window and what it's going to map to, it's now going to map to the second column, first row, and we're going to work out what the feature map value will be. So again, we're mapping the kernel across this and we're taking the dot product. So if we look at the first row, we've got 1 times 1, which is 1, 0 times 1, which is 0, and 0 times 1, which is 0. Then we've got 1 times 0, which is 0, plus 1 times 1, which is 2, plus 1 times 0, which is 0. And then if we look at the last row, we've got 0 times 1, which is 0, 1 times 0, which is 0, and 1 times 1, which is 1. Added to the 2 we have, that's going to give us a value of 3. So completing the rest of this feature map, we're going to leave for tomorrow's touch. You're going to work through this to work out the rest of the feature map. So you'll see we need one more value for the first row, and then we'll start moving down one row to work out the values for the next row. So this is basically what happens in a convolutional layer. The next layer that we're going to look at is your nonlinear or ReLU layer. So the main aim of this layer is to incorporate some type of nonlinearity, and the way that's achieved is by applying the ReLU function. So the ReLU function will basically be applied to the output from the previous layer. So that's usually a convolutional layer. So it will be applied to the feature map. And usually the ReLU function is a very simple function. It takes a maximum of 0 and whatever the function is being applied to. So the other layer that you can have in your CNN, and usually this is often applied, or this layer usually occurs after a nonlinear layer, is a pooling layer. And the whole idea is to ultimately reduce the amount of parameters that you're going to have going forward. So the way it does this is by actually reducing the size of the feature map, and there's different types of pooling that can be performed. So the very common one is max pooling, but you can also have some pooling, you can have average pooling, and the whole idea of pooling is linked to the size of the feature map that you want to be produced at this layer. So if you want a 3x3 feature map, for example, then the size of the rectangle that you take in the current feature map that you're going to actually reduce, that will actually map accordingly to the size of what you want to be produced. We'll look at the example at the bottom. So if you look at the example at the bottom, we have a 4x4 matrix, but we want to map that to a 2x2 matrix because we're using a 2x2 filter and we want to use max pooling. So what we do is every square of 4 then has to be mapped to one value. So that's you have the first square in the top left hand corner, second square in the top right hand corner, third square in the lower left hand corner, and fourth square in the lower right hand corner. And these will be mapped to different values. So if we look at the first square, if you're using max pooling, you're going to take the maximum of the values in that submatrix. So that matrix now has 1, 1, 5, 6, and the maximum value is 6. So the maximum value in the first row, first column of the resulting feature map is 6. So similarly, if you want to work out the value in the second column in the first row of the resulting feature map, you're going to actually apply your max pooling to the second square in the original feature map. So that has values 2, 4, 7, and 8. So the maximum there is 8. So obviously, if you were doing sum pooling, then you take the sum. If you were doing average pooling, then you take the average. And then so it continues like that. If you look at the lower left-hand corner matrix in the original feature map, you've got 3, 2, 1, and 2. So the maximum value there is 3. And then the last one is 4. Okay, so that's the pooling layer. The main aim of the pooling layer is to reduce the size of the feature map, and then indirectly then reduce the number of parameter values, that is weights, you need to find. So the final layer that's normally included in your convolutional neural network is the fully connected layer. And the fully connected layer, sometimes you may have two layers that are fully connected, not just the last layer, but the main aim behind this layer is to produce your output. So this is producing your output layer. And sometimes you could have the last two layers that are fully connected. In CNNs, it usually uses the softmax activation function. And if you're performing transfer learning, then this is the layer that's not frozen. So normally when you perform transfer learning, you use some of the architecture that you've actually used when applying your CNN to another data set. So some of the layers you freeze and the other layers you retrain. So usually when you're doing transfer learning, your connected layer and your output layer is usually the one that you definitely will retrain, that layer at least. So we've looked at the basic structure of a CNN. So usually a CNN is made up of hundreds if not thousands of layers, and these can be combinations of convolutional, nonlinear and max pool, or any other pooling function applied, repeated before it eventually gets to the fully connected layers. Usually you can actually create these from scratch yourself when you're working with a particular application, but a number of these neural networks exist already, these CNNs, and they contain a different architecture in terms of the number of convolutional, pooling, and nonlinear layers and fully connected layers they have, and where in the neural network architecture these occur. So is it at the shallow end or is it at the dense end of the CNN? And a lot of these architectures you'll see have resulted from the ImageNet challenge and people trying to actually win the ImageNet challenge. So the first CNN is the LeeNet CNN. AlexNet was one of the winners of the ImageNet challenge. GoogleNet was a runner-up, I think, in the same year. And then, no, sorry, it's the other way around. GoogleNet was the winner in another year, and VGGNet was the runner-up. And then ResNet was also a winner in one of the years. So these are different types of architectures that exist. You'll also see some of them have numbers attached to them. So VGGNet, now you'll see there's a VGG19, a VGG16. Similarly with ResNet, you get a ResNet 50. And that it has to do with dimensions in the neural network architecture. And we'll look at that some more. You're going to look at that as part of the tutorial tomorrow. A more recent neural network is something called a DenseNet neural network, and that's been developed by researchers working in the field. So a lot of these neural networks exist and they have been pre-trained on ImageNet. So a lot of times you don't have to use one from scratch. You can use an existing architecture. So Python usually provides libraries for this. You could also possibly use the pre-trained neural network that has some architecture already fixed and that you retrain just certain parts of it. And that is the whole idea of transfer learning, where you'll freeze certain layers and then you'll retrain other layers. So the main difference here is that you may have a particular data set that you want to apply the CNN to, but it doesn't contain the same images. So you could pre-train it on images from ImageNet, and that's what these libraries have. They have pre-trained images, pre-trained CNNs that have been pre-trained on images from ImageNet that you can actually apply to the particular application that you want to look at and with the particular data set that you're working on. You could also pre-train these neural networks on a particular subset of images from a publicly available data set. So a common one is when people are working with plant diseases or species of categorizing plants according to species, Plant Village is a publicly available image set for this. So you can do some pre-training on that. And then you may have your specific pictures that you've taken yourself that you want to match that against. And then you could then apply it to these images but not develop the architecture from scratch. Use transfer learning and use the pre-trained architecture. So I'll stop there for today's lecture. A little bit more of what work we're going to continue with CNN. So we'll just look at these architectures in a little bit more detail. That's part of the TAC tomorrow. And then we'll do some practical work with this. We'll then do a quick overview of LSTMs and autoencoders just so that you know what they are. We won't go into as much details as we've gone with CNNs, but just so you get an overview of what they are, because they're very popular deep learning neural networks as well. And then that will basically bring us to the end of the section on neural networks, which I'm hoping to finish by next week Tuesday, next week Wednesday at the latest. And then we'll start going on to decision trees and unsupervised learning. This lecture is the last section on neural networks. So we've looked at different types of neural networks. We've started off with the learning perceptron algorithm. which does simple classification, binary classification. We then looked at extending this to a multi-layer neural network, and we looked at the backprop learning algorithm. And then we started looking at deep learning, and last week we looked at convolutional neural networks. So this is the last section in deep learning. It's autoencoders. Now there are a number of different deep learning neural networks. We did a brief summary of them in the first lecture, but three of the most popular are convolutional neural networks, autoencoders, and LSTMs. We don't have time to go through LSTMs, so this lecture is going to focus just on autoencoders. As it's the last lecture on neural networks, it's not going to be a very long lecture, so I don't want to start a new section in the middle of the section. So the next section we're going to look at is other types of classifiers, and the next type is decision trees, and we're going to look at ensemble techniques where you can combine the decision trees to create random forests, and we'll do that in tomorrow's lecture. So this lecture will finish off deep learning, and we're looking at autoencoders. The practical on Thursday will be a practical on convolutional neural networks for you to use Python and libraries that come with Python to implement convolutional neural networks. So the main way in which autoencoders differ from the neural networks that we've been looking at previously is that these neural networks actually perform unsupervised learning. So if we look at our training set doesn't have any labels like we have a classification where the training instances in the training set have labels indicating which class an entity with those attributes belong to. Here we don't have any labels, and what's very interesting is that the inputs are basically the same as the outputs, and the same as in inverted commas. So usually your input that you get at the input layer, it's converted into some representation, basically the same input, and that's output at the output layer. So it's basically your same input, but there's something slightly different. For example, they may be compressed if it's an image, and that's produced at the output layer. So a classic example, so not all autoencoders aim for compression, but a classic example of using an autoencoder would be to compress images. So the number of pixels are reduced in the image in the output, but your image is still viewable. And the whole idea is to reduce the size of the image. Your autoencoders are made up of 3 layers. So your input layer, which represents the input that you want to change the representation of. Usually in the standard autoencoder, there's one hidden layer, and that's also referred to as the layer that will produce some code that will then convert that input into a format that you require for at the output layer. And then the last layer is the output layer. So one input layer, one output layer. Generally there's one hidden layer, but then your neural network's not deep in the case where you have one hidden layer. You just basically have an autoencoder. In order to have a deep autoencoder, you usually need more than one hidden layer. As I mentioned, your autoencoder consists of an input layer, a hidden layer, and an output layer. So when the neural network learns and training is performed, the training that happens between the input layer and the hidden layer, we say that forms the encoder. So what happens when the encoder is applied is your neural network is basically encoding the input, and it's producing some code that when that code is then applied, it will then decode that input to produce the output. Now the training that happens, or the learning that happens from the hidden layer to the output layer, we call that the decoder. So that code that's produced during the encoding process, that code is then applied during the decoding process to produce the decoded input at the output layer. So for this reason, your autoencoder can be thought of as consisting of 2 components, the encoder and the decoder. So the encoder is involved in encoding the input and producing some code. The decoder actually takes that code and applies it to then produce the output at the output layer by decoding the input. Now, if you're dealing with a neural network that has just a single hidden layer, then your encoder and decoder are partitioned like I just mentioned. but you could have more than one hidden layer, especially in a deep autoencoder, in which case both your encoder and decoder are made up of more than one hidden layers. So autoencoders basically are trained in the way that traditional neural networks are trained. You have some type of optimizer or learning algorithm, and that optimizer or learning algorithm determines the weight during training. But just remember now, when we do training, we don't have labeled data, so there has to be some way of measuring whether the output that you're getting at the end of that neural network, those activations, are achieving the objective of the function. And usually this is some type of measure of how accurately that input has been reconstructed based on what you actually want. Like, for example, if you want compression, do you get the same input but with a reduced pixel size? So like we've done with the other deep learning neural networks like CNNs, when it comes to applying your optimizer, the whole idea is the optimizer works out the error, and then that error is then used to update the weights. And to work out the error, traditional functions that have been used for autoencoders, commonly mean square error has been very popular to be used in this particular neural network. And then, of course, we looked at binary cross entropy before. That's also another function that's commonly used when you implement autoencoders. Optimizers generally used with autoencoders are the backpropagation algorithm and a stochastic gradient descent. And then there has to be some activation function that the weighted input values together with added to the bias has to be input to produce the activation for each neuron. And the commonly used activation functions for autoencoders are the sigmoid and the binary cross entropy function. If we look at the different types of applications that you can actually use autoencoders for, so the classic one is the one we spoke about, where you're compressing an image, and that image is then reduced in size. So the whole idea is to get a compressed image. It can also be used where traditional methods like PCA, principal components analysis, is used to reduce the dimensionality of data. So that's another common area. For information retrieval, it's also been used in that domain as well. So this basically brings us to the end of neural networks. The test will be up until and including neural networks, and decision trees will be then tested as part of the final exam for the module. So Thursday, like I said, Thursday's prep, we'll look at some of these applications for neural networks for deep learning using Python. And then in tomorrow's lecture, we'll start with decision trees.